This is a summary of the paper Tectonic Evolution of the Qilian Shan, an early Paleozoic orogen reactivated in the Cenozoic, written by Andrew Zuza and collaborators and published in GSA Bulletin in 2017. I will focus here on one specific part of this paper, which is the tectonic model for the Proterozoic-Paleozoic history of northern Tibet. The Qilian Shan, located along the northeastern margin of the Tibetan Plateau, has experienced multiple episodes of tectonic deformation, including Neoproterozoic continental breakup, early Paleozoic subduction and continental collision, Mesozoic extension, and Cenozoic intracontinental orogenesis resulting from the India-Asia collision. The goal of the paper is to better constrain this origin and the resulting closure of the Neoproterozoic Ordovician-Tilian Ocean. Detailed knowledge of the initial lithospheric conditions prior to India-Asian collision at 65 to 55 million years ago is required to test models for the Cenozoic growth of the Tibetan Plateau and advance our understanding of continental tectonics. To constrain that, they conducted an integrated investigation involving geologic mapping, uranium, thorium, lead, zircon, and monazite geochronology, whole rock geochemistry, thermobarometry, and a synthesis of existing datasets across northern Tibet. In this summary, I will focus on one of the outcomes of this data integration, which is their tectonic model for the Proterozoic-Paleozoic history of northern Tibet. So let's start talking about the model. In the Mesoproterozoic, passive margin continental shelf and/or continental slope sediments were deposited along the southern edge of the linked North Tarim-North China Craton. This margin faced the Tarim or Paleo-Chilean Ocean, and the sediments consisted of around 1.8 billion year and around 1.45 billion year detrital zircon grains derived from the North China Craton. Convergence of the continuous South Tarim Chidam continent and the closure of the Tarim Ocean was accommodated by north dipping subduction along the southern margin of the North Tarim North China continent at around 1 billion years ago. The evidence for the existence of the Tarim Ocean and Tarim Arc is the 1 to 0.9 billion years ago granitoid belt that is exposed throughout Chidam, the Qilian Shan, the Altintar Range, Tarim, and Tian Shan. The inferred suture and subduction system is exposed at Aksu in Tarim, where Precambrian blue schist rocks are presently observed. This inferred suture partially parallels and overlaps with the Qilian and Qingling sutures to the southeast. In the late Neoproterozoic, rifting of this joint continent initiated at variable times, resulting in the opening of the Paleo-Asian, Chilean, and Tethys Oceans, from north to south, respectively. Now it is useful to take a step back and go over the possible geometric configurations of the Kunlun, Chidam, Tarim, and North China continents presented in this paper. The Chilean origin resulted from the collision of multiple arcs along multiple sutures in the early Paleozoic. The location of sutures may provide the paleogeographic configuration of paleocontinents Tarim, North China, and Kunlun Chidam. To the southeast, it has been argued that the Chilean origin and sutures were laterally continuous with the Qingling suture, based on similar lithological assemblages and geologic histories. However, the northwestern termination of this origin and suture is not known. Three geometrically plausible models exist for its continuation, as shown in Figure 17c. First, it may continue into Tarim and be currently covered by Mesozoic-Cenozoic sediments, which is the contiguous South Tarim Chidam continent model. Second, it may veer to the south of Tarim and be overprinted by Cenozoic Western Kunlun and Pamir thrust belts, which is the separate South Tarim and Chidam continent models. Although evidence for this suture in the Alting-Ta range suggests that the suture cannot be that far to the southwest. And third, the Kunlun-Chidam continent may have only partially separated from Tarim, and the abrupt western termination of the Qilian suture represents the western extent of the Qilian Ocean, which is the peninsular Kunlun-Chidam continent model. Each of these configurations has implications for the nature of the Kunlun-Chidam continent, including its size, geometry, origin, and tectonic relationships between constituent blocks. For example, the contiguous South Tarim-Chidam continent model requires the southern portion of Tarim to have linked with the Kunlun-Chidam continent in the Precambrian and that an early Paleozoic suture traverses Tarim. The separate South Tarim and Chidam continents model is the only one that predicts the Kunlun-Chidam continent to be an individual entity surrounded entirely by oceans, and therefore presently surrounded by suture zones. Whereas the peninsular Kunlun-Chidam continent model requires a Precambrian linkage between Chidam and Tarim. They tentatively support the peninsular Kunlun-Chidam continent model, which is scenario 3 in figure 17c, but they emphasize that this issue is still unresolved. They support this configuration because of two main reasons. First, Precambrian basement of Kunlun-Chidam is similar to that of Tarim, North China, which indicates that these two continents may have been contiguous prior to Neoproterozoic rifting. Second, no Phanerozoic sutures or amalgamation structures have been reported between the Kunlun-Chidam and Tarim continents, which further bolsters their Precambrian connection. Now back to what was happening in the late Neoproterozoic, when rifting initiated at variable times, resulting in the opening of the Paleo-Asian, Qilian, and Tethys oceans. The earliest phase of rifting led to the opening of the Tethys Ocean, which initiated during or immediately following the early Neoproterozoic collision at around 900 to 870 million years ago, along South Tarim's southern margin. The opening of the Paleo-Asian Ocean to the north of the North China Craton occurred subsequently, as recorded by around 825 million years ago ultramafic intrusions and passive margin strata. The opening of the Qilian Ocean was preceded by bimodal volcanism from around 775 to 600 million years ago, and the deposition of passive margin strata. This rifting occurred subparallel to the early Neoproterozoic Tarim suture zone. As previously explained, they inferred that the Chidam and Tarim remained connected during the opening of the Qilian Ocean because there are no observed Phanerozoic sutures or amalgamation structures between these continents. The Kunlun-Chidam continent may have rotated away from North China as a peninsula that led to the opening of a westward tapering Qilian Ocean. This interpretation also suggests that the Qilian Ocean was a relatively small sea and not a through-going ocean separating Laurasia and Gondwana. They estimate the width of the Qilian Ocean using observed modern subduction rates typically of 1 to 5 cm per year, and based on the fact that the arc was active for at least 40 million years, that is from 490 to 450 million years ago. According to this, there must have been between 400 and 2,000 kilometers of the Qilian Ocean to be consumed in the Qilian arc. They find this width reasonable given that the Kunlun-Chidam continent was equal or longer than 1,000 kilometers. In the Cambrian, the Chilean Ocean reached its maximum extent, and subduction initiated along the southern bounds of this ocean. During nascent arc formation, the Chilean suprasubduction zone ophiolites were generated from around 540 to 500 million years ago to the north of the Kunlun-Chidam continent. Inherited zircon ages during this time recorded a complex process of recycling and influence of underlying and adjacent continental crust. During the Ordovician, the region experienced continued subduction and magmatic arc formation when the Chilean Ocean subducted beneath the Kunlun-Chidam continent. Continental subduction began in the early Ordovician as Chilean oceanic lithosphere dipped southward beneath the Chidam continent. The Chilean suprasubduction zone ophiolite abducted onto Chidam and was also simultaneously under thrust beneath the continent. These dispersed ophiolites are observed throughout the present-day Qilian Shan and North Chidam. Ordovician strata were deposited in back arc and fore arc settings to the south and north of the Chilean arc, respectively. During this time, fragments of the Kunlun-Chidam continent were brought to ultra-high pressure depths via the subduction channel. They were later exhumed to the middle crust via either diapiric or subduction channel flow, where they were juxtaposed against amphibolite-grade suprasubduction zone ophiolite rocks. A trench parallel intra-arc right-slip strike-slip fault developed within the Chilean arc, which is evidenced by the right lateral shear zone that is exposed in the central Qilian Shan. Ages from monazite grains included in garnet indicate that this shear zone was operating at around 480 million years ago. The kinematics of the Chilean strike-slip fault suggests right lateral obliquity during the subduction of the Chilean Ocean, which is consistent with counterclockwise closure of the Chilean Ocean. They propose that northward slab rollback at the south-dipping Chilean arc subduction zone occurred in the late Ordovician early Silurian. Northward slab rollback can explain three key observations. First, the northeastward Yanging trend of arc magmatism throughout the Qilian Shan. Second, the observation that late Ordovician arc plutons intrude Ordovician fore-arc strata. And third, the position of ophiolite fragments and ultra-high pressure rocks within and behind the Chilean arc. The arc may have propagated northeast over these features. By around 445 to 440 million years ago, the Tarim North China cratons collided with the Kunlun-Chidam continent. The timing of collision is not well constrained, but diffuse around 445 to 440 million year ago Plutonism was followed by relatively little magmatism based on previous studies. Also in this study, the youngest pulse of monazite ages corresponds to this time period. Also, Silurian strata have been classified as flysch deposits that transition to Devonian molasse rocks. In addition, during this collision, North China's passive margin strata were juxtaposed against the accretionary wedge, melange rocks, and ophiolite complex of the Qilian arc. Protracted convergence led to shortening and exhumation of early Paleozoic granitoids, ultra-high pressure rocks, and ophiolite suites in the Devonian. This protected history of two major ocean closure events in the Neoproterozoic and early Paleozoic was reactivated in the Cenozoic by focused strike-slip and thrust faulting. The main observations are that major left-slip faults of northern Tibet parallel Phanerozoic sutures. like the Haiyuan Fault, which parallels the surface trace of Qilian Qingling suture zone. In addition, the Neoproterozoic North Deeping and Early Paleozoic South Deeping subduction zones suggested in this work would provide subduction melange channels to focus Cenozoic shortening in northern Tibet. This may explain why significant crustal shortening across the Qilian Shan thrust belt occurs nearly 1,500 kilometers north of the Himalayan collisional front. And this was the tectonic model proposed in this paper by Zuza and collaborators in 2017, published in GSA Bulletin. The references used for the construction of this model are hereafter listed.